Gamma cameras are the most commonly used instrumentation for image acquisition in nuclear medicine. The imaging process begins when a radiopharmaceutical is administered to a patient. This occurs in one of three ways: ingestion, injection, or inhalation. Once the patient is injected, they are placed onto the gamma camera bed where they are positioned under the detector for imaging. A gamma camera detector is composed of a collimator, scintillation crystals, a light guide, photomultiplier tubes, and preamplifiers. The acquisition process begins when the gamma rays emitted from the patient interact with the detector's collimator. Collimators are used as physical discriminators, only allowing the desired gamma rays to enter the detector. To achieve this, the collimator's septa are composed of lead or tungsten, which eliminate any undesirable rays. It is important to ensure no scatter radiation proceeds to the scintillation crystals, as this can decrease image quality. The thickness and length of the septa varies depending on the type of radiopharmaceutical being clinically used. After the gamma rays have traveled through the collimator, they interact with the camera's scintillation crystals. These crystals are commonly made from sodium iodide doped with thallium impurities. The crystal thickness should be approximately 13 mm to ensure image degradation does not occur when the crystals are too thick, and to prevent poor detection efficiency of gamma rays caused when the crystals are too thin. Current scintillation crystals are hexagonal in shape, so they can be positioned close to one another, ensuring there are no gaps and all surfaces are covered. The scintillation crystals convert the gamma rays to visible light, which is then directed through a light guide to a photomultiplier tube. The purpose of the light guide is to direct the light to each PM tube to increase the efficiency of the light collection and image uniformity. Photomultiplier tubes, also known as PMTs, are stimulated to produce an electrical current pulse when light signals interact with the photocathode. The photocathode is comprised of a photoemissive substance that expels an electron when hit by a light photon. This expelled electron becomes known as a photoelectron and passes through a focusing grid which directs the photoelectron to the diodes. The diodes are a positively charged voltage metal that attracts the photoelectron. As the photoelectron moves from diode to diode, the electron is multiplied until it reaches the anode. The amount of signal amplification is between 3 to 6 times the initial input for each photomultiplier tube. Preamplifiers are another way to increase the signal output. From this point, the PM tube will direct a signal to the system's electronics. The signal is transferred digitally or electronically to a position circuit or energy circuit. The more modern gamma cameras operate through an analog to digital converter system, ADC system. This means that the PM tube output is directly digitalized through the system. These ADC systems are able to extract the position and energy data simultaneously. This approach improves errors caused by noise, pulse distortion, and pulse pileup. The final step to the image acquisition process comes once the images are generated on a computer monitor, where they can be constructed, altered, and generated.